Have you ever wondered how scientists manage to control the most delicate and elusive particles in the universe, making them perform complex calculations? Cryogenic cooling is the essential technique that achieves the qubit ground state by drastically lowering its temperature to near absolute zero. This extreme cold is absolutely critical because it minimizes thermal interference, allowing the qubit to settle into its lowest energy state, which is its stable and predictable starting point for quantum operations. The fundamental reason we need such extreme cold lies in the nature of thermal energy and its effect on quantum systems. At higher temperatures, atoms and their constituent particles, including the electrons that from a qubit state, possess significant kinetic energy. This thermal energy causes them to vibrate, rotate, and interact randomly with their environment, leading to a state of thermal excitation. For a qubit, thermal excitation means it is not in a well-defined quantum state, making it impossible to perform precise quantum computations. By removing this thermal energy, we effectively quiet the qubit, allowing it to relax into its lowest possible energy configuration, known as the ground state. This ground state is the pristine, undisturbed starting point from which we can reliably encode quantum information. Practically, achieving these ultra-low temperatures involves sophisticated technology, primarily dilution refrigerators. These specialized machines employ a continuous circulation of two helium isotopes, helium-3 and helium-4, through a series of chambers. By manipulating the pressure and allowing these isotopes to mix and separate, the refrigerator can absorb heat and reach temperatures as low as a few millikelvin, which is just a tiny fraction of a degree above absolute zero. This carefully engineered process creates an incredibly isolated and cold environment where qubits can exist in their delicate quantum states. One of the remarkable advantages of this extreme cooling is its ability to significantly suppress a phenomenon called decoherence. Decoherence is the loss of quantum properties, like superposition and entanglement, due to interactions with the environment. By reducing the thermal energy, cryogenic cooling minimizes these disruptive interactions, effectively extending the amount of time qubits can maintain their fragile quantum states. This extended coherence time is paramount for building complex quantum circuits and performing meaningful calculations before quantum information is lost. Ultimately, cryogenic cooling is not just about making things cold. It is about creating the foundational stability required for quantum computing. By bringing qubits to their ground state and protecting them from environmental noise, this technology enables the precise control and manipulation of quantum information, unlocking the potential for revolutionary advancements in computation and science.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.